All right, Algebra 1, here we go. Moving on 10-2, simplifying radicals. Our essential question today is, how can you simplify radicals using multiplication and division properties of square roots? Okay, let's start off talking about what is a radical expression. An expression that contains a radical, that square root symbol, okay? Like 2 square root of 3, that's a radical expression. The square root of x plus 3. As long as it has that radical bracket right there, then it's a radical, okay? Property for multiplication and division is this. With a and b both being positive, because you can't take the square root of a negative, okay? And they can equal 0. If you have the square root of a times b, you can split that up as the square root of a times the square root of b, okay? I'll show you how that works. And likewise with division. The square root of a over b is the same as the square root of a over the square root of b. So you can go either way with them, okay? We'll look at some examples of that. Something you're going to want to keep note of here are some of our perfect squares. So when you start talking about taking square roots or factoring out a perfect square, we got to know what a perfect square is. Okay, and we start with 1. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16, and so on, 25, 36. Those are the perfect squares. This kind of got brushed out a little bit. 144. 169 is 13 times 13, and so on. You could figure that out on your own and carry it out further if you like to. Okay? Those are perfect squares. So let's take a look at some examples here. Okay, we start out with, we want to simplify the square root of 48. Okay, 48 is not a perfect square. It wasn't on our chart there. But there is a perfect square that goes into it. Okay, kind of like when we're trying to find that greatest common factor, we're trying to find that greatest perfect square that goes into 48. That's a factor of it. And 16 times 3 is 48. If you have to, you can take that number and start dividing it by perfect squares. Does 1 go into it? Of course, we never really use 1, but does 4 go into it? Yeah, but is there something bigger? Then you try 9, then you can try 16 and 25, and then you get to the point where you realize that, okay, the only thing that's going into it is 16 evenly. Then you can split it up, that's 16 times 3, and you can take the square root of the 16, it's 4. So you get 4 times the square root of 3, or 4 square root of 3. Okay? Likewise here, 160. What's the biggest perfect square that goes into 160? Well, I know 16 goes into it, because 16 times 10. Does 25 evenly? No. 36? No. 49? No. And as you go up, you realize that the only thing that goes into it is 16 times 10. Okay? Evenly. Perfect squares. Okay? Which is the square root of 16 times the square root of 10. 4 square root of 10. Okay? 54. What goes into 54? Well, 9 goes into it. 9 times 6. Okay? And you also, now your n to the 4th, when you start looking at the variables and taking square roots of them, basically all you're doing is you're taking half of the exponent. Because we know that n squared times n squared is n to the 4th power, because you add exponents. So in essence, you're kind of just cutting it in half. So I can take the square root of the 9 and take the square root of the n to the 4th. I get 3n squared, and then the 6 stays inside. Okay? 72. That's 36 times 2. Okay? And you can work your way through it. 4 goes into it, but there may be something bigger, and you work your way up to 32. And some of these, get used to them, because you'll see these numbers over and over, so you get used to what goes into it. When your variable has an odd exponent, just drop it back 1. Okay? Because if it's an even, we know we can take half of that, but you can't take half of the odd one there. So you're just going to take 6 and 1. There's my m to the 7th. I just drop off 1, so I get an even. I can take the square root of the 36th. I can take the square root of m to the 6th. It's just going to be m to the 3rd. So I get 6 m to the 3rd. That's the square root of that and that. And the 2m, which I can't do anything with, stays inside. Okay? Here I've got a number outside. I'm just going to multiply it along just like I normally would. 80 I know is 16 times 5. You're used to it. T to the 5th becomes t to the 4th and t. Just drop it back 1. I can take the square root here. I can take the square root of that. It's just half of it. square root of 16 is 4, and when I bring it out and multiply by negative 2, I get negative 8. Okay, that's the negative 2 times the 4. Okay, the square root 4 right there. And then half of my t to the 4th is t squared, and then the 5t stays inside. Okay? Multiply and simplify. You multiply the outsides together, you multiply what's inside together. 9 times 14 is, or 7 times 14 is 98. 1 plus 2, that's t to the 3rd power. Okay, and then just like what I did right here, 98 is 49 times 2. T cubed, I'm going to make it t squared and t, just kick it back 1. I can take the square root of those two. The square root of 49 is 7 times the 6 is 42. T squared, half of that is t, and then the 2t stays inside. Okay? Division, same kind of deal. I can take the square root of both of those, they're perfect square, no problem. Two ways of looking at this, they're not perfect squares. Okay? One thing you can do is if you want to split it up, you can, just like it showed there. Okay? The problem with that sometimes is, and you know with fractions, you can simplify a fraction. Okay? You can split that up and try to work it out, but really the first thing you want to do is simplify the fraction first. Just like you normally would. So I would, instead of trying to continue to do this since they're not perfect squares, I would keep it like this and try to simplify. Okay? 2 goes into 8 and to 25, or into 50, so I end up with 4 and 25 right here. I took a 2 out of those two. And 3 over 1 with the x just leaves me with an x squared. Okay? I simplified the fraction first. Now I can take the square root of both of that. That's 2x and that's 5. And we're good. Okay? So always look to simplify the fraction inside first, and then go ahead and deal with the radical sign. Okay? The last thing, when you're looking at that division, sometimes you can't take the square root of what's in the bottom here. And we got to do what we call rationalize the denominator. Okay? Because we do not want a radical sign left in the denominator. Okay? 3 over 7, we can't do anything with that. It is simplified. But that means I got a square root of 7 down here. I don't want that radical down here. How do you get rid of it? Whatever the radical is, multiply the top and the bottom by it. Because in essence, when I multiply this by the square root of 7 over the square root of 7, which equals 1, I'm really just multiplying by 1. So I'm not changing the value, I just change the way it looks. Okay? And then I multiply straight across, outsides with the outsides, insides with the insides. And notice what I've done is I've created a perfect square here. I can take the square root of 49 and I get 7. If you can simplify the top, simplify the top. Okay? So here, as an example, I can't do anything with that. So I'm going to multiply the top and the bottom by that denominator. Okay? 7 times 8, that's 56n over 64n squared, which is just 8n. I know I'm creating a perfect square, so I can take the square root of it. This is in the radical, this is not. You can't put the 8 into the 56 because they're not both in the radical anymore. Okay? If it was, you could, but it's not. So you can't do it. This is, let's see, does 4 go into it? 4 times 14, right? The square root of the 4 is 2. The 14n stays inside. I can take a 2 out of this. I get the square root of 14n all over 4n. And that's it. Don't try to cancel the n's out. Don't try to take another 2 out of there because the 4n is not in the radical, and that is. So you can't do it. Okay? We're going to look at examples of this here over the next couple of days. So we'll get plenty of practice at this when we get back in here. All right, we'll see you tomorrow. Bye.